Good afternoon, everyone. We'll be starting class in 1 to 2 minutes' time. Alright, good afternoon, everyone. And in today's MATLAB session that we're doing today, we're going to be focusing on how do we go about finding zero crossings for a particular sinusoid, as well as how can we go about plotting a phasor using MATLAB in particular. So, as you can see here in my code editor, I already have some example code that was provided to you in your lab scripts, but I'm going to type in this code step by step here and explain what it does, so that way you can have a good idea of how things are done in such a step by step manner. So I'm just gonna blank off all of this, and we're going to see this step by step as to how it executes in order to understand what it is exactly that the code here is doing in particular. So the first thing we're going to be finding here is that we're going to be trying to find the zero crossings for any sinusoid wave. And of course, in doing this, that means we need to have a sinusoid wave to begin with. So let's set up our x-axis and sinusoid wave. So let's say x here is 0 to, with increments of 0.1, sorry, up to 4. And then let's say we have sine 1 here is equal to 10 by sine of 10 by x. And sine 2 here is equal to 42 by sine 6 by x. And let's create our signal. It's going to be the addition of these two sinusoids. And let's plot what our signal looks like. Plot x signal. Let's make it a little bit fancy. So I want it to be blue with O markers represented by a straight line as well. That's B, O, and a dash. And I'm going to hold my plot here before I move on with anything else. So the first thing that we're going to see here is that in setting up our sinusoid wave and adding them together, all we just made sure is that even though we have the addition of two sinusoids here, we're just going to observe what the plot is going to look like with respect to this for x versus our signal, which is the addition of the two sine waves. So if I run this code, you'll see here that we get this representing our addition of our two sine waves in particular. And we can see that the B, O here, and the dash in our figure, the O's are the markers for each one of the data points. The B represents that it needs to be the color blue. And the dash here represents the straight line that is going to be mapping for our entire graph. So the next thing that we're going to be doing here is that we're going to have to see, okay, we need to also plot our zeros here from our graph. So we're going to put in plot zeros on our graph. So we're going to put plot x, and then we're going to use a zeros function here in MATLAB, which finds the zero of any vector that we give it. And in this case, we're going to be using our x vector here. And we're going to put k here as our marker. And let's run this and see what it looks like this. So we're going to get our zero line here for each one of these points in particular, represented by this dotted line. This is a nice way of how to go about getting your zero line in a nice format in particular. So this comment needs to be updated to reflect this. Plot zero line x-axis. So the next thing that we're going to do here is that we're going to try to attempt to find our zero crossings here from our example graph. So we want to see here in our graph, where can we automatically find where we have these points here, where the graph is actually at the value of 0. And if we don't have these points, because remember this is a discretized time graph, how do we calculate for these points here? Because remember, in discretized times, if these points don't exist, we're going to have to do some sort of estimation in order to get them. So let's see if we can find the next point after our zero crossing. So let's call this sig pos, means signal position, and we're going to use a function here named logical. And what logical here basically does, it just looks for all the positions in the vector once a certain logic is satisfied. So you want to see once we have anything of values greater than 0 in our signal here, we want these to be marked with a value of 1. Otherwise, we want the values to be marked as 0. So, in the comment here, this is that we're basically finding all the positive points in our graph with this line here. And then the next thing it is that we need to find is our changeover points, which will be where the signal goes from positive to negative. So we're going to call this cross and say sig pos minus circ shift sig pos 1. Now, circular shift is a nice fancy function. Basically, that's going to assist us with us trying to find all these changeover points in particular. And if you want a little idea of what circular shift does, so we could help circ shift in our command window. And we can basically see in our example, what the circular shift does is that if we had a matrix here being 1, 2, 3, 4, 5, 6, 7, 8, 9, and we decided to shift it, it's going to shift all the first dimension values down here by 1. So instead of it starting with 1, 2, 3 as our top row, we want to shift all the rows here down by 1. So 1, 2, 3 will now be our second row, 4, 5, 6 will be our third row, and our initial last row here will now be our first row as well. So circular shift just basically is a nice way of shifting our values for any given signal that we obtained. In this case, we just want to shift the signal by one particular value in our circular shift and make sure that instead of it overflowing, the end value will just go back to the starting in our signal to begin with. So once we have this, let's actually put this on our plot and see what it looks like. So let's put plot x and logical cross. For that's all for x-axis, and signal logical cross. there. Let's give it some markers. So that's k0 this. Let's see what this looks like. So at this point, we don't really see anything that seems to be standing out on our graph. And the reason for that being is that it's going to be a little bit hard to see here, because some of these points here are actually black now instead of blue. So we can see, like here, this one is a little different color, this one here is a different color, this one here is a different color, and these basically represent the points that we're going to be looking at for when we went from positive to negative in our single graph that we generated. Now, this still isn't good enough because, like I said, this is a discretized time graph. And in some cases, those values weren't actually at 0. We saw that it may have been slightly above 0 or slightly below 0. So we're going to have to do an estimation here to figure out what's the value of the graph is going to be actually at when the y value here is 0 in particular. So we're going to do a little bit of fancy code here. And this is what we refer to as a straight line approximation estimation. So straight line approximation estimate, and let's call this cross index equals to find cross. So basically, this find function here is going to find all the x coordinates or the x indices of our cross signal that we had here, which would be our changeover points that we estimated earlier. And we're going to need a count here to keep track of how many x indices that we found. So let me just put some comments here. Find x indices of our crossover points, and then keep a count of how many crossover points are found. And we also need to make sure that we store this in a vector of x values. So vector of x values here for cross points. Let's call this x0. And we're going to say NaN 1, n cross. Now, you probably want to know what is NaN. So let's see, help NaN. So NaN is basically means that once it's not a number, and we do a track within our n cross here, we're going to store these x values here to do a tracking for our crossover points in particular. So to do the estimation here, we're going to have to use a for loop. So I'm going to say for AA equals 1 up to n cross. Let's say this cross here equal to the cross index of AA. So this basically gives us a track to be like, okay, for our current value that we're going to be using in our n cross vector, we want to store this in a temporary variable named this cross to basically keep track of where we are. And then we're going to do what we refer to as linear interpolation to estimate what is our x coordinate value for when y is 0. So we're going to call x1 here equals to this cross minus 1. And this will be the point before crossover, i.e. before crossing the x value. And then this other thing that we're going to be using, we need an x2 value here. So we're going to see the point after crossover, after crossing the x value. x2 here is going to be this cross. And we also have to do this similarly for y values. So the point before crossover, i.e. before crossing y value. So this is going to be y1 is equal to signal this cross -1. And the reason why we're using this crosshair -1 is basically to keep a track of where we are. To know, okay, this is actually the point before we go from positive to negative, and this is the point where we actually went negative in particular, or vice versa if we're going from negative to positive. So we need to associate this index here for x1 and x2 with our y1 index here for our signal that we had. And similarly, we also have to do this for after crossover. So the point after crossover, i.e. after crossing y value, y2 here is going to match with x2, so it's going to be signal this cross. Then we have to do our interpolation equation to do our approximation, interpolate between these two coordinates, find 0. So we use a fancy function here equals, well, I'm just going to ratio, and we're going to say 0 minus y1 divided by y2 minus y1. And then we need to get an estimate of our x value. And we're going to call this x0 AA. Equal to x of x1 plus our ratio multiplied by x of x2 minus x of x1. And we're going basically just going to keep on repeating this throughout the entire graph until we get all the points that we need. So we end off loop there. Let's add this to our plot to see what it looks like. So add to plot to show our 0 crossings. And in this case, we're going to be using our x0 vector. So we're going to put plot x0. We're going to need the zeros from 1 to n cross that we had to begin with. And let's give this a new color. So let's say red and mark it with O's as well. And okay, this should run. Yes, it did run. So if I run this here and see what it looks like, you can see that now I have some red circles. And these red circles, if I click on them, gives me an estimate of our x and y values for where the graph actually crossed at the 0 line. So we can see here, for y equals 0, we have an estimation of what the x value is here. Same thing here, for y equals 0, we have an estimation, and so forth as we keep on going. So that fancy piece of code there basically does a nice estimation because of the nature of the discretized time graph that you're dealing with. Wherever we don't have y equals 0, we need to estimate what it's going to be using the point before our crossing and the point after our crossing. In particular, if we're going from positive to negative, or in this particular case, the point before crossing to the point after crossing when we are going from negative to positive. And this fancified code here with all the nice comments basically does this estimation for you. Now, the things to note here is that in our workspace on our right hand side here, we do have some of these vectors that are stored and some values that are also stored here. Now, the important vector that we need to watch at here is our x0 vector. So if I double click on this x0 vector, you want to see that we have some values here. So like 0, 0.4839, 1.08, and so forth, right? And this x0 vector here maps to each one of these points where y is equal to 0. So you can see here for this one, it was 0, 0, 0. This one here is 0.4839. Expand this a little bit. Yeah, so you see this was 0.4839. We have the direct value here. Next one here was 1.0869, and so forth. So basically, we have an entire vector here containing all our x values for when y is equal to 0 for this entire graph using our estimation techniques. And once we have this x vector here, it's possible for us to use this in order to go back and reformulate certain aspects of the wave. So let's say, for instance, if we had an arbitrary sinusoid wave, and we know that it only contains one period or one frequency, but we don't know what that period or frequency is. So we know basically period and frequency are related to each other where t is equal to 1 divided by f. And if we know that wherever the graph crosses here at y equals 0, that we are able to obtain a corresponding x value for our x-axis here, it also means that once we know that the graph has crossed twice, but a particular sine wave that only contains one frequency, we just need to get the second x value here in particular and subtract it from the starting x value that we had. So the second x value to the first x value, well, the zeroth x value, okay, I'm saying that wrong. The third x value that we have here to our first x value that we obtain as a result. And once we have this, and we're able to subtract these values, we basically obtain the periodic time. Once we have the periodic time, it's just 1 divided by that periodic time to obtain the frequency of our graph. So that's important to know, in particular, how to go about extracting period of any sinusoid graph that is given to you once you don't have the equation. You basically use that piece of code that's provided to you in your lab script, and once you do have that code here to get each one of the x values here for when y is equal to 0, you know that if the wave here only contains one frequency, it's okay for you to go about getting the time here, and then once you have the time here, you subtract it from the first instance after the wave has crossed twice, and you're able to get your periodic time, and then you're also able to go about obtaining the frequency. So just to give you an idea of how we actually can do this, let's modify our code a little bit. And let's say I don't have this signal here. I'm going to create my own signal. So let's say signal here is equal to, let's say 32 by sine, let's say 16 by x plus 15. Let's run our code here to see what it looks like. So let's see, I did get an error which basically says array indices must be positive integers or local value. Okay, so let's see if that plus 15 threw me off a little bit. Nope, that plus 15 did not throw me off. What did I do wrong? Right, let's do an estimator to see what's going on. Alright, so I know what I did wrong. And it's a typical mistake that we did see from beforehand. The first instruction that we must always have in our scripts, because we have working variables here on our right hand, that we need to clear everything before we run. Okay, it doesn't seem like that. Let's see, clear that out of the way, run. Seem to be fine here. Okay, estimator. Put back as is. Should it run? Yes, it will run as normal. Okay. So let's recreate this. Signal 10 by sine 10 x. All right. Okay. So let's see what error it is that we're getting here. So it says the array indices must be positive integers or logical values. So the error it says here is at line 48, where we add signal this cross minus 1. So this basically tells us that because this crosshair is starting at a value of 1, we need to make sure that once we're going here on line 48, this means this crosshair needs to be starting at a value of 2. So maybe this needs to go +1, let's see. And then we have an estimation error here going about doing this. So index and season number better than name, index must not exceed 14. Okay. Alright, so let's troubleshoot this and see what's going on. Cross index here is that. It's like our original error. The estimation error here is where from this guy. Alright, so let's start troubleshooting. AA is 1 to n cross. Okay, n cross has 14 values. Right, that's correct. Right. Have this failure signal here. Alright. So x1 is at 0, 1. Alright. The x1 here shouldn't be at 0, x2 here should be at 1. Alright, so let's watch this step by step and see where it is that we actually get in our error. So I'm going to reset this. I'm going to use some debugging tools here to actually figure out what's going on in particular. So we want to see what happens in our first iteration of our for loop. What is going to happen in particular. I'm going to run up to here. And I want to see what values we have here for x1 and x2. So see in this iteration here, when our for loop only runs once, x1 and x2 has a value of 1 and 2. And it having a value of 1 and 2, that means it actually starts correctly as of such. And this crosshair actually has a starting value of 2. AA here is at 1, which is correct. And the cross index is what we actually have to observe here, which starts our loop here. So that's why we have 250, 110, 159, and so forth. So this is what we actually have to look at in particular. So let's stop this, and let's put back our signal to where we are getting our errors. Signal equals 10 by sine, 10 by x. Let's clear our workspace. And let's see what's happening here. So I'm going to run up to right here before we get our error. And let's see what's going on. So in this particular case, we had a 1 by 14 double, which is fine. A was still 1, our current index was fine. Okay. So this cross was actually started at 1 here in particular. So that's what we don't want. We don't want this cross here to start at 1. We want this cross to actually start at 2. And in doing so, we need to make sure that in going about doing this, that in order for it to start at 2, we watch the behavior of our for loop here to go about doing this. So basically, in doing this, this is what we have to pay attention to in order to go about making sure that this code here won't have any particular errors. So what I'm doing here is with respect to us doing our analysis here for our MATLAB 2B exercise in particular. So I'm showing you guys how to go about troubleshooting the code as of such in preparation for MATLAB 2B. So you'll have to pay attention here because when our code doesn't run, we have our graph here starting to look kind of weird, and stop this here. So if I run up to here and I observe this cross here is starting at 1. But we don't want this crosshair to start at 1, we want this crosshair to start at 0. Because when we had it in this case, stop this and then run up to here, this crosshair actually had a value of 2. So we don't want all of this to run in particular when this happens. So let's try put it in a condition inside a loop and see what happens. So we want to say if this cross equal to 1, we don't want to do anything, so we'll just put some blank value here. If this cross 2, else, and let's run all of this here. Tap this end, and hopefully it runs. All right, nice. So it does run. So we basically see here that we're able to get our 0 crossing values respectively for what we required. Now ignore this other graph here in the background. That was our previous graph. You can ignore that for the time being. We don't really need that. The graph we're paying attention to is just our single graph here that we had. So if I clear this, I think the graph might still. All right, yeah, here we go. Correct graph. Right. So we can see here that we do obtain our values as of such, and in this particular case, we can see that from starting from 0 here, and our second x value is 0.628317. If we wish to find what's the period of a graph, we can say, let's say t here, and this particular set of values here is stored in our x0 vector. We open up this x0 value vector, we can basically see what it is. So we need to pay attention to where we won't be extracting our values because our first value here was not a number. So we want to say t here is equal to x0 of 4 minus x0 of 2. And we have t is equal to 0.6283, and then f is equal to 1 divided by t. And we see here we get a frequency of 1.5916 Hertz. So this is a nice way of going about doing your estimates and so forth in order to go about obtaining the frequency of a graph from any sinusoid that's given to you in particular. There is a little bit of code troubleshooting that you may have to do. In this particular case, we also saw that where we had the signal here, for a single signal, we had this crosshair starting at 0, and that's what we didn't want from the error that we just now saw. So we need to just put in an if statement here to prevent that, and then we can just go about doing whatever we need to do. Even if I put this here, like so you're saying this crosshair is equal to 1, and let's just run this code. You'll see that we'll still get the same results altogether for obtaining our vector values. That we absolutely need. And then we can see x0 here. Even if we have not a number, we can also do a check here to see how we can reduce this. So let's say if x0 of 1 is equal to not a number, we want to remove this value. So we want to say, get a little bit of help here. So give me a second. This value array. You can say brackets, I'm using the wrong syntax. x0 is equal to x0 of 2 up to x0 to length of x naught. That should run. So I'm going to test this out here because I already have my x naught value. So x naught is equal to x naught of 2 up to the length of x naught. Right, and I get rid of the not a 0 value. So that will be fine if we do this check here. So once we do that check, we basically go about doing the elimination process as required. I can rerun this. Are we basically okay? Have it here. There's probably my conditional statement that is giving an error. Play this and check this back. Alright, so that's my conditional statement. That seems to be giving me an error. Let's see what is going to on with my conditional statement. See what I can do to this. I might need to use a specialized function in order to achieve this. So let's see. I may need to use an isNaN function. So help isNaN. True for not a number. All right. Say if we run isNaN x naught of 1. Right. So I'm going to have to use this. So I can't use this logic here. So I have to say isNaN x naught of 1. Hopefully that should truncate it. All right, yes, because I'm using capitals, so that should be common. Okay, so all right. The last thing I need to do here is that after I do my plot, I need to move this code and then truncate it. I can't do this before my plot because of the error that popped up here. And so let's truncate x naught vector. This value is not a number. Run this, and then we're pretty much okay. All right, nice, we're good. So we still have our values here. And then in our x naught vector, we have our truncation here. So then we can go about just writing code. And we don't have to worry about looking for the positions here in order to calculate our periodic time for any sinusoid that we have. All right. So that basically gives us an idea of how to go about modifying a code for when we start dealing with single frequency waves and how to avoid any particular errors that we did occur here inside our MATLAB code to go about checking what we did, how to go about troubleshooting it, and so forth. The first error that we got was that in this particular case, when we had moved from a combination of two sinusoids to just a single sinusoid, we saw that the value of this crosshair in our for loop went to a value of 0. And when we had, went to a value of 1. And then when we reached here where we were going signal of 1 minus 1, which would be signal of 0 in brackets, MATLAB was giving us an error. Because in any vector MATLAB doesn't start from an index of 1. MATLAB doesn't start from an index of 0. MATLAB starts from an index of 1. So in order to prevent this, we put in this if logic here to say, okay, if this cross gave us a value of 1, we just put in a dummy value here, just say this cross equals to 1. We could have put this cross equals to any sort of value. And then for the else statement, we run our code as is. The second thing we had to watch out for is that when we did this and we did our plot, we saw in the x0 vector that we had here, the first value would have shown up as not a number. And in order to eliminate that, we have a specialized function here named isNan, which is not a number, and we check the first value in our x0 vector. And if it is, then we truncate out that value. So we just start from the second value up to the end of the x0 vector, and we store this as our new x0 vector here. And that basically takes care of all the error troubleshooting that we have to watch out for, in particular when you're going about doing this code here for exercise 2b later on. So the code here that you see in this demonstration, in this tutorial, is what actually is going to be the corrected code that you will have to use throughout in your application for exercise 2b later on. The second thing that I have to show you guys here, and this is going to be quite quick, is how to go about doing a phasor plot. And phasor plots basically rely on coordinate geometry, where you know the start point and the end point of your line, and you're given a given length about your line. Basically, the length here is going to be the magnitude. Once you have these things, you can basically go about saying, okay, I know these things, I can formulate what's going to be our phasor and what it's actually going to look like. So I am going to have to bring up my whiteboard here. Second. Right, this is from last time, so let's clear this. Okay. So for your phasors, basically, it's going to be your standard axes that you are accustomed with. But instead, let's say if we had a line looking like this, your phasor most of the time is going to start from 0. And it's going to have some endpoints here. And the angle of phasor is from the positive real axis. This is real, and this is imaginary. Our angle here, represented by theta, would be that particular angle. So even if we had like a phasor that's like something like this, the angle for this phasor here in red is going to be this here. So this could be theta 1. And the angle basically goes anti-clockwise in particular for that particular case, for any phasor. So erase this and make things look a little more neat. So for our simple case, when we have our phasor basically starts from the origin. It goes up to some set point here. And we need to know what's the angle, which is referred to as the phase. So the length of the phasor is what we refer to as the magnitude. And theta here is what we're going to refer to as the phase degree. And in order to plot this, we need to know what the magnitude and the phase is accordingly as of such. So this is actually going to be a little bit of your homework before trying to figure out what's going to be the equations here in order to get this. But once you have the magnitude here, and you know your start point here is going to be 0, 0, up to some set magnitude, and you have your angle at which it occurs, there's a possibility for you to get the end point here. Let's call this xy. You can calculate for xy here using these two values. So this is actually going to be a little bit of your homework to establish the relationship between the magnitude and the phase of your phasor to get the end point for any phasor that you're dealing with. Going back into MATLAB, what this code does is that it takes those 2 points that you had, so like the start point for your phasor, and then the end point for the phasor, and it can find the difference to get the magnitude, or you can just provide the magnitude accordingly, if you wish. And if we run this code here, we see here that it will plot our phasor for us accordingly, with the start point, the end point, and the magnitude accordingly as of such. Now, note that this code here does not contain anything regarding the phase. And that also is going to be a little bit of your homework. How do you incorporate the phase here in order to go about getting this phasor in particular? You do have the magnitude, and like I said, we were calculating the magnitude here by just doing the difference between the 2 points. But how do we incorporate the phase as a result? And the hint here is that when you find the endpoint here for your phasor, you will have already incorporated the phase of the phasor to go about doing this. So that's going to be a little bit of your homework to do. And at the end of your 2A exercise here, there is a practice exercise that incorporates the interpolation code that we saw earlier and this phasor plotting code that we are seeing here now. And you're going to have to do a little bit of work in order to figure out what are going to be the math equations to go about incorporating them here in your code. And once you have these equations, how you go about getting these particular things. Now, the interpolation code that we had here earlier, this is basically somewhat completed with all the fixes and so forth that we just now had. So you don't really have much to worry about this. You'll be using the interpolation code in order to find out what's going to be the frequency of your waves that is given to you, as well as it can also be used in different ways to actually find the phase of your wave. But I'm not going to tell you how to find the phase of the wave using this. I actually want you guys to do a little bit of investigation and see how actually you can incorporate it to find the phase. So like, let's say if I put plus 15 here, and this plus 15 here is basically somewhat like your phase of a wave. And if I check what this looks like here, you can see here instead of starting at 0, we start at some other value. How do we incorporate these x values here to find what's the phase of our wave instead? So that's something to think about. How do we use these x values here to figure out what's going to be the disposition of our sinusoid wave, because it's no longer starting at 0. The plot code that I gave you here, you're going to have to figure out how to incorporate the phase in order to find the endpoint. Because you know your starting point for your phasor, you need to incorporate the magnitude and phase to find the endpoint of your phasor. And once you're able to do that, and you get the endpoint, the code here will handle the rest in order to plot the phasors here for you. Alright. So, there are 2 scheduled demonstration sessions for this particular lab. And the reason why there are 2 scheduled demonstration sessions is because you do have a little bit of homework to do, to formulate your equations and so forth, and to do a little bit of troubleshooting to see what goes on here and what you might need a little bit of help with. I am highly advising you guys to post on the forums once you start doing your work and you start encountering errors and you don't know how to resolve them. Post it on the forums. If you need any particular help, you can directly email me. If it's something that I cannot assist with on those scheduled demonstration sessions, I will help you guys on those sessions. For whoever posts on the forum, who directly emails me in a one-on-one for you to actually fix out your errors, and let's see how we go about troubleshooting this and for you to resolve your stuff. But it is quite important that you do formulate your equations beforehand, especially check this back to tell you which equations. You need the equations for establishing the frequency of the sine wave, which we just now saw here for the interpolation code, establishing the phase shift of the sine wave, so that one you actually have to do a little bit of work for, and then also establishing the magnitude of your phasor. But establishing the magnitude of the phasor is going to be quite simple. I'm not going to tell you how or why it is quite simple. I'm pretty sure you can guess how it is going to be very simple in particular once you start doing any sort of phasor calculations as of such. Alright, so once again, I'm saying make use of these 2 scheduled demonstration sessions. Post a lot of stuff on the forums. Directly email me if you have to, if you're not comfortable with other people seeing what you're doing. And if it's something I cannot answer immediately, I will schedule it in for those demonstration sessions for you to get some one-on-one feedback where you show me what you're doing, and I'll be able to help you at that point. Like I said, make full use of those 2 scheduled demonstration sessions in order to go about troubleshooting this and so forth. Alright, so I know it was a little bit complex today and so forth. Are there any particular questions before we close off today's session? So the logic behind the interpolation code basically is just for us to figure out, okay, we're dealing with a discretized time signal, and let me just run this guy when you need the graph as illustration here. We can see here that these 2 points here, these do exist in discretized time, but without these 2 points, there isn't a point here that exists for where y is equal to 0. So the question is, how do we use these 2 points where it's 1 after y equals 0 and 1 before y equals 0, do an estimation to obtain the value of x when y is equal to 0. So I explained the logic earlier as to how we go about doing this in particular and as such, but basically once we have all the positive points here and the changeover points, we then go about doing that estimation here that went on and so forth. So basically, once we do have those two vectors, the positive points and the changeover points, we do the estimation here using this entire for loop, where we do find those points and then we do an approximation in between those 2 points to go about doing it. As of such, once we do the estimation here, all the values are stored in this x dot vector for your corresponding x values for your y is equal to 0. And once you have that, and it's stored in this vector, you're able to access this at any point in time to get the corresponding x values for your y is equal to 0. There were 2 things I fixed there. We had an initial error where this cross here would have initially obtained a value of 1. And then when we go down here to this y1 signal would have been 1 minus 1, being an index of 0. That's something you don't want in MATLAB because indices for any vector start at 1 and they don't start at 0. So that's why we put in this logic here by this if statement to check if it's 1, just to store any random variable or any random value in this cross, and then continue on with our entire logic. The second thing was that inside the x0 vector here, there may be some cases where the first value here will show up as not a number. And in that particular case, when it's not a number, we need to make sure that we remove that number, that not a number, sorry, from our vector. So we use the isNaN function here to check if it is not a number, and then we just store the rest of the vector back into x0 here, thus truncating the first value out entirely. The linear plot code here And all this code here is basically provided to you in your two-way script, with the exception of the fixes that we saw here in the video for our linear interpolation. Uses two coordinate points to plot a straight line between these 2 points in particular. It is important that you establish a mathematical relationship for you to establish what's going to be the phase of your vector. And once you have that phase and you know the magnitude of the vector, being the magnitude of the sine graph, and you have this math equation to establish between the magnitude and the phase, you can then establish what is going to be the endpoint here for your vector. And once you have your endpoint here in coordinate geometry being xy coordinates, you're able to plot your phasor as of such. Alright. Any further explanation? Like I said, it was recorded earlier when I was going in depth. So once you go about watching back the recording for when I was discussing the logic for this for loop here, which is basically all the inner workings that you're going to need, you're pretty much okay. And if it's something that you don't understand, feel free to ask about it, and I will give you some more further explanation regarding it. Alright, any further questions? Alright, doesn't seem like I've got any further questions at this point. So like I said, make full use of the demonstration sessions. Make sure that you guys post a lot of questions for stuff once you're trying to establish your math equations and so forth. Anything that you do get stuck with, post it on the forums or directly email me if you're not comfortable with other people seeing what you're working on. Perfectly fine. If it's something that I cannot immediately resolve, I will schedule in guys for the demonstration session, and we can go about doing a one-on-one in that particular case to go about resolving it. Signal logic. Alright, that's the last question I'll be taking before I end. So you're talking about the signal logic for this cross. If you tell me which line number, that helps me quite a bit. Okay, nice. Oh, the circular shift. Alright, so let's see what this looks like here for me to give you a better explanation. So let's run up to this line. So the signal that we're watching here in particular is going to be signal position. And if we watch this, we basically see that wherever there are ones here, let's go back on our editor. Signal position here was to find all the positive points in your signal. And wherever there was positive, you want to mark that as a 1. If it was negative, you want to mark that as 0. So that's why when you're inside here, you see 1, 1, 1, 1, 1, 1. These were positive points, and then we had negative points here and so forth. When we circular shift, so I want you to keep an eye at this. So watch here. 8 here was 1, 9 was 0. When we do the circular shift here to find the changeover points, so let's run up to here. Let's watch back signal position. 8 here is 1, 9 is 0. But if we actually do the analysis lower down, we're going to see that some of these points here where we had 1 and 0 is actually going to shift. So what that logic does here is that when you do the circular shift in particular, this is to actually check to see once we shift this by 1 and we do a subtraction from the original signal, where it is that we do establish that these crossover points actually do occur. So I'm just going to call this sig temp equal to circ shift sig plus 1. And if we watch sig temp here, you can see here 8 here is 1 and 9 here is 1. If you watch our normal sig, 8 here is 1 and 9 here is 0. So if we do a subtraction of these in particular, these make sure that we do establish where our changeover points actually do occur. So I'm going to stop this, and that's clear. And let's run back up to this point here. So remember, sig plus here was 1, 1, 1, 1, 1, 1, 1, 0. And the next thing we want to watch here, what's going to be cross. So if we check crosshair, you want to see crosshair is going to mark off where we do have these signal changes. So positive 1 would have been that it would have been from positive to negative. Negative 1 would have been a change from negative to positive, and so forth. So all that line there just basically does is that it makes sure that we establish where these crosses occur. And we need to mark this off as a positive 1 and a negative 1. Alright, nice. Okay, so like I said, if there are anything that you guys do need to ask, feel free to ask them on the forums or directly email me. You can ask in the comments down below if you wish. If it's something that's a little bit sensitive and you don't want other people seeing your work, directly email me. I will address you guys accordingly. So that way you're able to see how it is what problems we are getting in particular when you're going about doing this, as well as what sort of assistance you guys do require. I take full advantage of the 2 demonstration sessions as of such. If it is something that I cannot immediately resolve, like I said, I will schedule in you guys for that demonstration session, and we can have a little bit of one-on-one feedback in order to resolve what's going on. Alright, so like I said, make full use of those demonstration sessions, because we do have 2 scheduled, and it's because this exercise is a little bit tedious. It's not too difficult, but once you understand what's going on, it makes things a lot easier. But the only way for you to understand that is that you need to actually start doing some of the work to establish the mathematical formula, and then how to go about mapping the formula back into your code workings and so forth. Alright, so until our demonstration sessions, take care, be safe, and I will see you guys soon. Later.